We're in chapter 4, section 4, and we're going to talk about the mean value theorem for integrals. So just like we had one for derivatives, we have one for integrals. There's also an average value theorem and the second fundamental theorem of calculus, which is not going to be the same thing as the fundamental theorem of calculus. All right, so let's talk about mean value theorem first. Remember with derivatives, trying to recap. With derivatives, we said that if f is continuous and differentiable on an interval a to b, then there must exist some f prime of c for which that derivative, that tangent slope, is equal to the secant slope between the endpoints b and a. Has to be true. There's somewhere where we can come up with that tangent slope being the same as the secant slope. For integrals, we're saying that there's got to be some c value for which the area of a rectangle with base a to b and height f of c, that area is equal to the area underneath the curve. You can kind of see it visually here, right? This area has this chunk that is outside of the function, but it has a symmetric chunk of area underneath the function that it's leaving out. So by having it out here and including in its overall area, you're getting the same area, right? So there's some sort of rectangle, the height of which falls between f of a and f of b, where that rectangle has the same area as the area under the curve from a to b. So the theorem officially says if f is continuous on the closed interval a to b, then there exists a number c on a to b such that the integral from a to b of f of x dx, the area under the curve, is equal to, what's f of c times b minus a? Remember on our diagram, f of c is the height of the rectangle, b minus a is the length of the rectangle. So there's some c for which the area under the curve equals the area of the rectangle. And let's just make a note. Height is f of c. Base, I should probably write base, is whatever the distance between b and a is. Just like the first MVT, mean value theorem, that we had for derivatives, it's just an existence theorem. It doesn't tell you what c is. It just tells you that, yes, c must exist. All right, so we'll practice that in a little bit. What's this average value? You'll see this pretty commonly on AP questions for your response. It says if f is integrable, that's a fun word. If you can take the integral of f of x on a to b, then f average, this is the notation for saying average value, of f is 1 divided by b minus a, so 1 divided by the length of the interval you're looking at, times the integral from a to b of f of x dx. And that's equal to some f of c value. Okay, so what the heck is this saying? Remember, average and average value, we're saying average function value. We call that f average, but it's also known as just some f of c, right? There's some c value, there's some f of c, for which the total area divided by the total delta x reaches that average value. So like if the f values range from 0 to 20, we want to find out what is the average value. Is the average value 10? Is that the height that's average? Or is the average value 15? What is it? It depends on the function itself. Well, think about what this formula is actually saying. It's saying, first, find the integral, which is the total area under a curve on the section a to b, and 2, divide it by or multiply it by 1 over, divide by b minus a. Or, in other words, that's the total delta x, right? Total change in x is whatever the length of b minus a is. An average is just adding up how many numbers you have and dividing by how many there are. We're adding up the total area and dividing by the total delta x that we're looking at. It's going to give us an average value. And again, this f of c that our answer comes out to is you can think of it as average output. It's an average function value. Average y value. Lots of different ways to think about that. So let's find the average value, and they'll actually use that terminology on the AP test, of f of x equals 3x squared minus 2x on the interval 1 to 4. We can see that the values of f of x range from 1 to 40. What is the average value? All right, so let's use our formula. The average value, f average, is equal to sum f of c. I don't know what c actually is yet. Of what? 1 over b minus a. So 1 over, we're on the interval 1 to 4. So 4 minus 1, so 1/3, times the integral from 1 to 4 of 3x squared minus 2x dx. Let's work on this. 1/3 times what? 3 times x cubed over 3 is x cubed. Minus 2 times x squared over 2 is minus x squared. Evaluate from 1 to 4. When you plug in 4, you get 64 minus 16. Minus, when you plug in 1, you get 1 minus 1. 1/3 times 64 minus 16 is 48. Minus 0. 1/3 of 48 is 16. F average, or f of c, is equal to 16. So there's some c value for which the average height is 16. Is 16 the dead center of the range? No, it goes from 1 to 40, and 16 happens to be the average value. All right. So did we find c? No, we found the average value. The average value is 16. If it said find where that occurs or find the x coordinate for which we have an average value, then you would set your function equal to 16 and solve for x. Whether that had to be done on a calculator or not, we could find out. According to this picture, it looks like it's going to be something just short of 3. I don't necessarily want to take the time to figure out what it is, but you can always pause the video and do that on your own. Next example, given that the integral from 3 to 6 of x squared minus dx equals 57, they just gave you the total area right there. They did all that fun, hard work for you. Find all the c values that satisfy the MVT for the function on 3 to 6. All right, so what is this saying? What is that MVT? Remember, MVT is saying, hey, there's got to be some c value where on 3 to 6 where the f of c, go back to reference this, where the f of c times the b minus a equals that area, right? So let's see. F of c times b minus a is supposed to equal the integral from a to b of f of x dx. Let's just copy that down so I don't have to keep scrolling. Do we know f of c? No, because f of c is just the thing that we're trying to find here right now. Okay, but we do know b minus a. 6 minus 3 is 3. And we do know the integral from a to b of f of x dx. We know that that integral is equal to 57. I can find what f of c is equal to. So what's 57 divided by 3? 19? Yeah. So there's some f of c value that's equal to 19. The question is, find all the c values. All right, well, f of c is saying there's some C value on 3 to 6 for which the function x squared minus 2 equals 19. So now I take it there. X squared minus 2 is supposed to equal 19. That means x squared is supposed to equal 21. And that means x could equal plus or minus square root of 21. Now the question says we need to be on the interval 3 to 6. So I can't have plus or minus. Only x equals square root of 21 is on the interval 3 to 6. So x equals, I probably should have said c equals. I should have probably said c squared, whatever. Does that matter? No, not really. Square root of 21 is your answer. All right, moving on. What's the second fundamental theorem of calculus? So remember, the first fundamental theorem of calculus, the original FTC, is the one that says, hey, the integral from a to b of f prime of x dx is equal to f of b minus f of a. Remember that one? If you take the integral of a derivative, you're going to get the actual function, and it's going to come out to f of b minus f of a. Okay, so that was the original one. The second one says, oh, sorry, there's a recap right there for that. My bad. The second fundamental theorem of calculus is thinking about the definite integral as a function rather than a number. So sorry, that's one more thing I should have said. When we do f of b minus f of a, yes, we get a numerical value. So the second fundamental theorem is still thinking of taking an integral of a function and getting a function back, but it's a little bit different. You're going to have different bounds. Instead of your a and b being numbers, a constant and a constant, your a will be a constant and your b will be a variable. Sometimes it's just x, and sometimes it's more complicated than that. So the upper limit is some sort of variable or expression. And I know in our first fundamental theorem, I just wrote it as f prime, so I could say f of b, f of a. If it's just written as f of x dx, then it's equal to the antiderivative of b minus the antiderivative of a. Okay, so let's say we're taking the integral of just some function. And the function variable here, with respect to that variable, needs to be different than this variable here. That's important as well. The area function that you're getting, g of x, that variable matches that upper bound. Okay, so I sort of did this in pieces, but again, to look at what does this theorem actually say when we put it all together? You're getting some sort of an area when you integrate, right? Instead of the area being a number, the area is 12, you're getting the area as a function. So the area is this function as we move x along whatever our interval is going to be. So the integral is a function of x, and x is the upper limit of the antiderivative. When we get an answer, our answer isn't going to be a number. Our answer is going to be some sort of function, and it will be in terms of x, even though the original function was in terms of t. So that all seems very confusing. Let's try putting it into practice a little bit. So evaluate the function, the integral from 0 to x, cosine of t dt, at x equals 0, pi over 6, pi over 4, pi over 3, and pi over 2. So before thinking about the second fundamental theorem of calculus, we could do this as 5 separate problems. We could say, what is the integral from 0 to 0 of cosine of t dt? And if I think about that graphically, I could say, oh, the integral from 0 to 0 is 0, right? We had that rule. I could say the integral from 0 to pi over 6 of cosine of t dt and keep going. Instead of doing that, it's easier just to fix x and just let x be sort of like play the constant role for a minute and then apply the fundamental theorem once. So instead of having to do 5 different definite integrals, I can come up with a function or an equation for the area under that curve. And then when I plug in an x into that function, that's what the bounds were. It was from 0 to whatever I just plugged in for x. All right, so what are we talking about? Let's just put this into practice. What's the antiderivative of cosine of t? Should be sine of t, right? Plus c if it's indefinite, but we have a definite integral. We are evaluating this from 0 to x. Okay, well, if we use the fundamental theorem of calculus, that should come out to the sine of x minus the sine of 0. Oops, I wrote theta, I meant 0. What is the sine of 0? Oh, that happens to be 0. So what we're saying is the area under the curve is equal to sine of x. And then wherever you want to set the limit, going from 0 to 0, 0 to pi over 6, 0 to pi over 4, whatever you want to plug in for x, you take the sine of that value, and that will be the area underneath that curve. So here's the graph of cosine of t. And again, we can say, oh, well, I can visually see that the integral from 0 to 0 of cosine of t dt would be 0. But I can also say sine of 0 equals 0. Here I can say sine of pi over 6 equals 1/2. So when I put in the pi over 6, wherever that falls, that area is equal to 1/2. When I do pi over 4, sine of pi over 4 is radical 2 over 2. When I do pi over 3, sine of pi over 3, trying to shade in as I go, is radical 3 over 2. And when I get to pi over 2, the sine of pi over 2 is 1. That's the end of this little interval, I'm assuming. So, yep, because that's where the cosine graph would have hit 0. So that whole thing shaded has an area of 1. So it's faster to just come up with the antiderivative in terms of x, and then use that antiderivative as your area formula and plug in various values of x. And remember, you're allowed to do that because this formula was based off of the beginning of the interval being 0. So g of x, which is our area, calling it g of x, is equal to the integral from 0 to x cosine t dt, which comes out to sine x. It's the area under the curve of cosine t from 0 to x. As you change x, which is the upper limit, the area, which again in this case was g of x, changes as well. G of x is accumulating area in this case. The area was getting bigger as we went from 0 to x. What if we rewrite the second fundamental theorem of calculus? So if f is continuous on an open interval I containing a, then for each x in the interval, the derivative with respect to x of the integral from a to x, f of t dt, should just be f of x. Now, why is that happening? So we know that derivatives and integrals are inverse operations. They cancel each other out. But like what happens to this t, right? Remember, the integral from a to x of f of t dt is some function g of x. Whatever that area function's variable is, it will match the upper limit. It will not match the different variable that was in there to start with. So I could say this is the same as the derivative with respect to x of that g of x, that antiderivative that we got, which was an expression of x. And if I take the derivative of an antiderivative, well, that has to be the same as f of x. Because everything's with respect to x now. And if I undo the operation that I just did, I'm going to get back to f. But it won't be f of t. It'll be f of x, because that's what I've plugged in so far. There's sort of a corollary here. And this is important. This is like a super important corollary. It's not always going to be this nice, neat little x. Remember when we started with derivatives before chain rule ruined our lives, right? Before chain rule came around, We were taking derivatives, using power rule, product rule, quotient rule happily, and all of the little nested functions were x's, or maybe an x plus 2 or something like that. But it was 1x. And so we didn't have to worry about chain rule. And then all of a sudden we started doing like sine of 2x or sine of x squared or whatever. And that's when we had to think about chain rule. The same thing is true here for the second fundamental theorem. So here's a corollary. The derivative with respect to x of the integral from a to, let's just call it lowercase g of x, because I don't want to use an f. So this is anything, like lowercase g of x is like 2x or x squared or square root of x or, whatever, x over 3, I don't know. Anything other than anything whose derivative wouldn't just be 1. So it's g of x, and then we've got some f of t dt. What would that be equal to? Well, normally, when we take the integral from a to x of f of t dt, we get f of x, right? We get some sort of function in terms of x. Well, here it would be some sort of function in terms of g of x multiplied by chain rule g prime of x. Oops, extra parentheses where I didn't need it. And why did I just get back to f? Like, why didn't I have an f prime here, whatever? Remember, the derivative and the integral are canceling each other out. So even though you first get an antiderivative, when you take the derivative, you're going to get right back to the original thing. So you're going to have an f function, but what's going to be inside of it? Not a t, not just a plain old x, whatever you had up here, whether this is an x squared or a 2x or whatever. And then since this is something other than just x, you've got to have a little chain rule multiplied to it as well. If you want a proof for a sort of proof for why that's happening, let's kind of think about this as an antiderivative. So when I take the integral from a to g, I get the antiderivative of g of x minus the antiderivative of a, right? And then when I take the derivative of the antiderivative, I'm going to get some sort of f of g of x. But then I've got a chain rule in there, g prime of x. And remember, f of a, antiderivative of a, is a constant. When I take the derivative of the constant, that's minus 0. So yeah, this simplifies to f of g of x times g prime of x. Let's put this into practice. Find the derivative of g of x, which is the integral from pi over 2 to x cubed of cosine of t dt. All right, now we're not taking, we're going to find the derivative. So let's say g prime of x. What is it supposed to be equal to? It's supposed to be equal to f of x. Now f of x, this is f of t right here. Here's f of t, dt. So I don't need to think about what's the integral of cosine and then take the derivative of that. I'm just going to say, hey, if I take the derivative with respect to x of both sides here, then those are going to cancel out. I'm going to get cosine of not just x, I'm going to get cosine of x cubed. And then I need to remember chain rule to say, oh yeah, multiply it by the derivative of x cubed, which is 3x squared. Right? So my answer for g prime of x, remember, I'm not supposed to get a numerical answer. I'm supposed to get a function because I have an upper limit that's a function, not a number, is cleaned up 3x squared times cosine of x cubed. Can I verify this to make sure it's true? Let's just double check here. So let's go ahead and actually take the antiderivative. Let's integrate. Let's see, the integral of cosine, what's the antiderivative of cosine? Sine. Evaluate it from pi over 2 to x cubed. That means I should get sine of x cubed minus sine of pi over 2. And that's sine of x cubed minus 1. That's the antiderivative. Now I'm supposed to turn around and take the derivative with respect to x of both sides. So, sorry, my work's a little bit sloppy here. What's the derivative of sine x cubed? Derivative of sine is cosine of x cubed times chain rule, 3x squared. And the derivative of the constant one is 0. So I get the same answer that I had here. But rather than doing all this fun antiderivative work, I can just get right to the bottom line and get right to the answer using that second fundamental theorem. You don't have to verify or prove it on the AP test. You can use the second fundamental theorem and write the 2 steps that I did here. All right, this video, I'm not sure, I can't see the time on it. We may be getting long, maybe not, but in class, if we get cut off, you'll be finishing this for homework, but we'll just continue on. So here's some more integral practice, and we can use calculators. The temperature in degrees Celsius of the water in a pond is a differentiable function W of time t. The table above shows the water temperature as recorded every 3 days over a 15-day period. Part A says use the data from the table to find an approximation for W prime of 12. Show computations, indicate units of measure. All right, so part A, W prime of 12, we're trying to approximate it. It should just be, I think that you're allowed to use any 2 values to find the secant between, but it would make sense to use the 2 that surround W of 12. So I'm going to say it's approximately equal to W of 15 minus W of 9 over 15 minus 9. You could probably also, though, use like 15 to 12 or 9 to 12. We can check the scoring guidelines on that. So let's see, that's 21 minus 24 over 6. Negative 3 over 6 is negative 1/2. We need units, and we've already shown our work. These are temperatures in degrees Celsius, and we're talking about days, degrees Celsius per day. Okay, part B. Approximate the average temperature, W average, not average change in temperature, but average temperature in degrees Celsius of the water over the time interval from 0 to 15 days using a trapezoidal approximation with subintervals of length 3 days. So they want us to use our average value formula, but instead of just integrating, because we don't have a formula to integrate, right? We get to use Riemann sums with trapezoids. So, all right, so average temperature, W average. Let's write it out with the integral formula. It's equal to 1 over 15 minus 0 of the integral from 0 to 15 of whatever, it's not, well, let's see. Sorry, of WT dt. Okay, so 1/15. Excuse me. All right, and then when we're talking about trapezoids, remember every trapezoid formula is 1/2 times delta x times the sum of the bases, W1 plus W2, whatever it's going to be. So everything's going to have a 1/2, and everything's going to have a delta x, delta t in this case. Delta t is 3 days, so 3/2. So I would factor that out right away too. So everything's going to have a 3/2. And then what are the bases that we're going to use? They want us to use every 3 days. So like one trapezoid goes from 0 to 3. One trapezoid goes from 3 to 6, 6 to 9, 9 to 12, 12 to 15. We should have 1, 2, 3, 4, 5 trapezoids And remember, when you're adding up trapezoids, some of the function values are going to get doubled. So we're going to have w of 0 plus 2 w of 3 plus 2 w of 6 plus 2 w of 9 plus 2 w of 12, but then you should only have plus 1 w of 15 because the endpoints, those bases, do not get used twice. The 3 and the 15 can go ahead and reduce. So we've got 1/10 on the outside here. And then let's put in, show those values. So 20 plus 2 times 31 plus 2 times 28 plus 2 times 24 plus 2 times 22 plus 21. And calculators allowed on this one. So I'm going to hop over to my calculator. Go. All right, I'm going to add up the values first and then remind me to divide by 10. I guess it's less typing if I just double these, isn't it? Double 24 is 28 plus 44 plus 21. Divide that by 10. 25.1. Remember, this is W average, and it's an approximation. I probably shouldn't have used equal signs there. Is approximately equal to 25.1 degrees Celsius. It's not a rate, it's an average temperature. All right, part C. A student proposes the function p given by p of t equals 20 plus 10t e to the negative t over 3 as a model for the temperature of the water in the pond at time t, where t is measured in days and p of t is measured in degrees Celsius. Find p prime of 12. Using appropriate units, explain the meaning of your answer in terms of water temperature. Now, calculators allowed, which is a good thing because we have not talked about how to take the derivative of e to the something or any exponential. So when you're doing this on a calculator part of an AP test, you can just do in your calculator, p prime of 12 is equal to or about equal to. You just hop over to your calculator. There's no work to be shown here. All right, so I'm trying to get P in my view here. All right, so math 8. With respect to x, our function is 20 plus 10x times e to the negative x divided by 3. When x equals 12, I'm just doing a quick check. 20 plus 10x e to the So I'm getting negative 0. Sorry, I'm getting negative 0.549. Oh my gosh, 0.549. There we go. Degrees Celsius per day. It says using appropriate units, explain the meaning of your answer in terms of water temperature. So remember, this is the derivative, which is the tangent slope, also known as a rate of change, instantaneous rate of change. So we're saying I'm going to say instantaneous rate of change. You need context. It says in terms of water temperature, of the water temperature in the pond on day 12 is a decrease, since it was negative, of 0.549 degrees Celsius per day. I think it's important to have the word decrease instead of just saying the average rate or the instantaneous rate of change is negative, blah, 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 because the whole point is like, what does that negative mean? And assuming you can interpret your units correctly, what does that mean? All right, part D. Use the function P defined in part C to find the average value in degrees Celsius of P of T over the time interval from 0 to 15 days. So the average value of P average, is equal to, we want the value over the 15 days. So 1 over 15 minus 0 times the integral from 0 to 15 of P of T. I paused for a minute because I thought for a second, I was thinking use your answer from part C, and that didn't make any sense to me, but it's just use this equation that we gave you in part C. You could also just write P of T dt in here. I just kind of like to show it to find this average value. So again, we're going to go over to our calculator and just say, type this all in. So math 9 from 0 to 15. Now, I didn't put in the 1 over 15 yet, so I've got to remember to, I got all excited to type this in. I want to remember to divide by 15 at the end. So just the integral itself is 386, but then again, you're dividing by 15. So I'm getting 25.757. And this is degrees Celsius because, again, that's the average value for this P function. And we just had to find it. We don't really have to interpret it beyond, of course, you should always label everything. But beyond that, we don't have to explain. All right. A roast at 160 degrees Fahrenheit is put into a refrigerator whose temperature is 45 degrees Fahrenheit. The temperature of the roast cooling at time t at the rate of negative 9 e to the negative 0.08 t degrees Fahrenheit per minute. Temperature of the roast is cooling. Find the temperature of the roast 20 minutes later. So the temperature of the roast is, let's just call it T. Oh, no, they use time T. We'll just call it R for roast. So we want R of 20. This isn't asking for an average value. This is saying, you know what temperature the roast started at. Find the temperature by finding the change in temperature 20 minutes later. So 0 to 20 of, I'm just going to call this R of T. So I don't want to write the whole thing out. R of T dt. Well, we know the roast started at 160 degrees plus that integral. So R of 20 is something. Let's see, 160 plus the integral from 0 to 20 of negative 9 e to the negative 0.08x dx. So 70.213. And the label on that is degrees Fahrenheit. Does that answer make sense? Yes, the roast is put in the fridge. The fridge is cooling down the roast. The roast should be cooler than it was when it came out of the oven. Did we use the 45 degrees? No, that's somehow factored into this given function, I'm assuming. All right, last example. The rate of change of the weight of a pig is given by 50 divided by square root of t plus 1. That says minus t on the end, where t is the time in months since birth. If the pig weighs 18 pounds at the beginning of its second month of life, find the weight of the pig at the end of its second month of life. Okay, so the beginning of its second month is, let's go back here. W of 0 is birth, right? Birth weight. So during its first month, your integral will be 0 to 1. That's during its first month, right? It'd be whatever its birth weight was plus the first month of growth. So we want the end of its second. So we want W of 2. That's going to equal, we don't have birth weight, but we have how much it weighs at the beginning of that second month. The weight at the beginning of the second month is the same as the weight at the end of the first month, plus the change in weight from 1 to 2 of, I'm just going to call this WT dt again. All right, so it is 18 pounds plus the integral from 1 to 2 of, fine, I guess I'll write it, this guy, dt. 18 plus the integral from 1 to 2 of 50 divided by square root of x plus 1, get out of that, minus x dx. So W of 2 is about equal to, what was it, 48.284 pounds. Let's have a little bit of a recap here, kind of an overview. Going back all the way to the beginning of the year. So if you have a quantity like f of x, and you want an average value of that quantity, so you want an f average or an f of c, average value, then you need to find 1 over b minus a times the integral from a to b of f of x dx. If you have a quantity, f of x, and you want to find rate of change is either a, rate of change is a tangent slope. I was going to say either tangent or secant, but I saw my second line there. You want a tangent slope, you need to find f prime of x. If you have f of x and you want to find an average rate of change, you're looking for a secant slope. And we find secant slopes by doing f of b minus f of a over b minus a. No calculus involved. That's just find the slope between two values. If you have a rate of change, you have a derivative, and you want to find a change in the quantity, so you have a rate of population growth, you want to find the population, change in population, that's a definite integral. So you need to find the integral from a to b of that derivative. And that will equal f of b minus f of a. If you have a rate of change and you want to find a function for that quantity to represent that quantity, then you need to use an indefinite integral, which would just be the integral of f prime of x dx, and you're going to get f of x plus some c. Use dh dt and f of x dx to help with units. So it's just always a good idea to write out your units for all of these problems. So like taking derivative with respect to what, or integrating with respect to what, makes a difference if you're trying to figure out your units. All right, that is it for today.